So our second talk for this evening, guys, if you can take your seats or at least be quiet, please. Our second talk for this evening is on the topic of interpretable machine learning, presented by Anthony Tockar. Anthony is a director and co-founder of Verge Labs, a new type of AI-focused company on the applied side of machine learning. A jack of all trades, he's worked on problems across insurance, technology, telecommunications, loyalty, sports betting, and even neuroscience. He's a qualified actuary and completed an MS in analytics at the prestigious Northwestern University. Please welcome Anthony.
Hi everyone. So I'm going to talk today about interpretable machine learning, which is an increasingly important topic, and one that I think most data scientists should have in their toolkit, if not all data scientists. All right. So interpretation is the process of giving explanations to humans. So a lot of the stuff we do is all very much in front of the screen, but guess what? It has to be interpreted into value and into dollars. So how do we do that? At the end of the day, a churn model, accuracy is important, but really what the client wants to know is what are the factors that drive churn? What's actually driving this? What can I do? What actions can I make to actually change this result and get my customers not to leave? So how did I do that? I looked at variable importance. A lot of packages in R, Python, other machine learning libraries will give that just straight out. So looking at different kind of importance of various features that go into your model, obviously. And sensitivity analysis. So that one wasn't that straightforward for me at the time. I remembered it from my early days as an actuary. Actuaries would often set a few assumptions and then tweak them slightly, things like inflation, interest rates. So I thought, well, that worked pretty well back then, so why don't I do something similar for these guys? And knowing obviously that the amount of sensitivity would change by the magnitude of the coefficient, but still quite useful and still quite a good way to view these changes. Sorry, screensaver. So then last year, ICML, just show of hands, who went to ICML last year? Yeah, so very much a leading machine learning conference. We're very lucky to have it in Sydney. And one of the first days, I think it was the first day actually, they had a workshop on machine learning interpretability. And that was led by a team from Google Brain. So, pretty cutting edge stuff. So what did they talk about? What were some of the techniques that came up with? Sensitivity analysis. Sweet, okay. Well, that means that I was on the right path. Mimic models. So if you had a complex model like a recurrent neural net or something like that, or even a random forest, well, just put some surrogate in there. So train a linear regression anyway, or train a decision tree or something anyway on that same data. At least that will give you an idea of some of those causal, well, maybe not causal, but some of the features driving the model. And then investigating hidden layers. So, if you're using a neural network, you can look at what's happening at each layer, and there's a few different ways to do that. But all in all, I kind of felt like, okay, well, this project was quite difficult because of the difficulty in interpreting this model. I've now seen the cutting edge. I was pretty much doing something close to that, and they still didn't really get it. So, quite difficult. I got a conclusion there. It's a link. I'll share these slides afterwards. You can check it out afterwards. But really, the conclusion is they maybe weren't ready for this kind of model. So yeah, war stories. There's lots of them in Sydney. Interpretability matters. So, all right. I feel like there's more to the story, and it's really starting to come through now. Sorry, let me just catch up on this side. So yeah, traditional model validation only tells us how we did on the holdout set. So it doesn't tell us whether our model's right for the right reasons or wrong for the right reasons. So the reasons for this are things like fairness. So you want to make sure that predictions are unbiased and they're not discriminating against protected groups. So I'm sure we've seen things like Cathy O'Neill's weapons of math destruction, a lot of the stuff on racism and bias within models. Now, an interpretable model can tell you why it decided that a certain person is not worthy of credit, for example. Makes it easier for you to judge for a human if the decision is based on a learned demographic bias. Quite important. Privacy, so regulatory reasons, privacy. GDPR, of course, coming in now. Everyone's starting to take notice. There's a weird little clause in there about the right to explain. It hasn't been fleshed out exactly, but one could definitely foresee there being breaches or lawsuits, things like that, around explaining your models, not just using black boxes kind of willy-nilly. And obviously, ensuring that sensitive information is protected. If you can interpret your model, that can help you. That goes a long way. Reliability and robustness. So, testing that a small change in the input doesn't lead to a big change in the prediction. Trust and causality. So causality I'm not going into in this talk. Interpretability and causality are linked, but they're definitely not the same thing. And I think it's kind of beyond the scope of this, but certainly kind of trusting a model. So, understanding, humans can trust something that they can understand. It's harder to trust a black box. You can look at something like accuracy, but there's things in there which you might not get, no matter how well you understand the algorithm. So certainly being able to interpret a model better improves the trust. So here's an example. This was, I don't know what COMPAS stands for, but it was a risk score that was applied in the US to, I guess, criminal offenders and what their likelihood was of committing a future crime. So we had these two people, obviously one's white, one's black, and so the guy on the left, Vernon Prater, he was rated a low risk. The girl on the right was rated a high risk. What happened subsequently? Well, he committed a grand theft auto, I guess. He had more prior offenses. Her offenses were quite minor, yet she was rated as a high risk. And yeah, as I say, subsequently, we found out that the model was incorrect. I mean, obviously this is anecdotal, but this was quite a big kind of scandal, I guess, in the US at the time, because these models were clearly there was a demographic bias to some of these models. And, obviously they weren't using race as a factor, but there were a whole lot of proxies that were being used for that. Another famous one this is a husky classified as a wolf. So, I mean, I'm no expert on these things, but I guess that's a husky. And so, sure, you can use kind of convnets, you can use really strong, powerful computer vision techniques, deep learning models, etc., to classify images. I'm not sure if this one's from ImageNet, but anyway. And when they looked at what was actually causing this particular model to classify it as such, these were the features that came out. So some of you might have seen this before, but really what's pertinent here is you're not really getting the animal at all. You're getting the snow. So the reason it's classifying this as a wolf is because there's snow in the photo. Which actually I found is quite a funny one, because I would associate huskies with snow, but never mind. So in response to this kind of stuff, it's starting to come out a lot more, driven by things like GDPR, driven by the fact that data science has often been difficult to productionize in a lot of businesses, and people are starting to realize that, hey, black boxes aren't all that. We need to be able to explain these things. So this is just a graph of the number of research papers kind of coming out, and it's obviously growing year on year. So there's stuff happening in the space, and even where we were last year at ICML, there's a lot that's happened, and that's obviously what I'm here to talk about. All right, so interpretable models. So we all should be relatively familiar with these. If you're not, I suggest you become familiar with them. They're very core to a lot of this data science skill set. Linear regressions, linear models. So the interpretability side of it is, as I've kind of mentioned before, for an increase in the numerical feature by 1 unit, the outcome is the coefficient. Similarly, for logistic regression, of course assuming like a linear function, we look at something called the odds ratio, but it's a very similar interpretation. So all that's happened is you've kind of squeezed this into a logit function. So if you just go through the example that I've got there, if you have odds of 2, it means the probability for y1 equals 1, so the class you're trying to classify, is twice as big as y1 equals 0. If you have a beta of 0.7, then it's a kind of exponential of that, and so it increases to about 4 times. So again, depending on the coefficient, but a linear relationship there. Decision trees are a bit different, but also highly interpretable. Even when I think of the very first model that I ever built, predictive model that I ever built, the first thing we did was just create a classification tree and look at some of those features, and those were the features that fit into our GOM. So, you know, it's a popular technique for kind of figuring out things like interactions as well as key variables. So, very simple interpretation, you follow the path, it shows you how the prediction is being formed. And it's obviously visual, so quite good from that perspective. Should be looking the slides up. Here's just a bit of a summary of some of the models that I guess you class as easily interpretable. So you'll see they have a lot of features, things like monotonicity, of course whether they're linear, and obviously whether they work for regression classification or both. So these are the popular ones. I'm sure there's other models out there, but you know, these are ones we're probably all fairly familiar with. So this is obviously something that I found. I don't know if it's that easy to just plot these things on a graph, but it's a broad kind of classification of how predictive some of these models are. So, you know, linear regression decision trees, I guess you call weak learners, and they're kind of to the left of the accuracy spectrum. I mean, yeah, I didn't make this graph. I've certainly been in situations where linear regressions can be a lot more powerful. But yeah, obviously as you get towards the more complex, the models become more accurate. However, they become less interpretable. You get that black box. So really what we're seeking is something that does both. So is there anything that does that? Sorry, lost my mouse.
Some suspense.
Yeah. Well, you've got to wait for each window to load up as well now. All right, so here are some model-agnostic methods. So when I say model-agnostic, I mean you can put any model in. So it doesn't matter if you've got a 40-layer deep neural network or if you've got a straightforward decision tree. These methods all work. Obviously, they might become a bit more difficult to interpret with a more complex model, but the output looks the same in every case. So feature importance, I've briefly talked about that before. As I say, a lot of packages will do this for you automatically. But what it'll allow you to do is you calculate the increase of the model's prediction by permuting the feature. And there's a few different methods of doing this, and I'm not going to talk through all of them. But really, you know, you can see on the graph there, it shows the relative importance of that feature. And so that means, you know, how important it is to the model. It doesn't tell you the magnitude. Sorry, it tells you the magnitude. It doesn't tell you the direction of the importance. It doesn't tell you that much about the relationship, but it's a start. You know, particularly if you're looking at things like overfitting or pruning variables, it's a good place to start. Partial dependence plot. A lot of you who've worked with neural networks would have seen this kind of thing before. It shows you, I guess, think of a partial derivative. It shows you what happens when you change just the one feature and hold the others the same. What this plot will do is it averages that over the entire set. So it kind of gives you one relationship between that feature and the predictor. So I think in this example, sorry, I can't see, it's too small on my screen here, but you might be looking at something like age and you'd expect that that's not a perfectly linear thing. So it can show you that relationship. So very useful from that point of view. Then you've got ICE, individual conditional expectations. That's actually very similar to the partial dependence plot. And again, there's a lot of different flavors of it. But what it will do is rather than kind of averaging of everything, it looks at the local point. So if you look at one particular data point and see how, if you hold everything else the same and change that one variable, what the effect of the predictor is, that's exactly what this graph is showing you. And it's just doing that for a whole lot of different data points. So you can see the shape, but you can also see if, you know, there's other interactions, other correlations and things in there. And again, there's different flavors of it. So that particular graph I don't find so helpful, but perhaps if you kind of have it all start at the same point and kind of go out in different directions, you can see a lot more. So again, I encourage you to look into it if you're interested. And then there's other methods. So, surrogate models I talked about already. Straightforward sensitivity testing, still very useful. Shapley values, GoldenEye, something I still want to look at actually. Loco, there's some stuff out there. But the main one I actually want to talk about today is Lime. So, sorry, just bear with me. Okay, so Lime stands for Local Interpretable Model-agnostic Explanations. So what does that mean? So first of all, they're surrogate models. So similar to how you might plot a decision tree over all your data, that will give you kind of one big average model. What Lime will do is it emphasizes the locality. So it looks at each particular data point and it fits a model to the points around it. It doesn't do this similar to PDP or anything like that. What it actually do is generate new points. So as it kind of says here, what you do is you start off with a point. You generate, based on a kind of normal distribution or some kind of statistical distribution, you generate random points around it. Based on a kernel that you can set, you can look at how to weight those points. So the closer, the higher weighting, and you fit a model to that. So that model will usually be an interpretable model. Well, it should definitely be an interpretable model. So you've got it. There's packages out there in R and Python now already that do this, that will allow you to fit linear models. I think the Python package now allows you to fit a decision tree as well. So, obviously two different types of interpretation. And certainly where you have kind of step functions and things like that, decision trees are going to be a lot more useful. So yeah, it's actually pretty simple, but it's incredibly effective. So here's I'll just talk quickly through how it might work, a bit more visually. So if you look at panel A there, it's predicting, you've got this kind of black box model. I think this one's a random forest, and it's predicted this kind of upside down V, and call the blue class 1 and the gray class 2 or class 0. So a linear model is obviously not going to cut it here. So then to interpret it, what it'll do is it'll generate, as you can see in slide B there, it's just generating a whole lot of random points around that. So it doesn't restrict itself just to the points in the model, because obviously there's quite a lot of issues with that you bring in a bias. So it's generated all these points, but then in panel C there you can see it's actually weighted it around the specific data point in question. And then what it does is it just builds a nice little linear model to capture that relationship. And so you can see it's kind of built a little classifier in there for that data point. And so what that allows you then to do is do something like sensitivity analysis and actually see what the effect of that is at that point in the model. So that's the theory. I didn't want to get too technical today, but feel free to hammer me at the end of the talk. I wanted to actually show a demo of a piece of software that I've developed for this. So I thought I'd go with something very current, which is, and yeah, I can't help it being a South African cricket supporter. Just have to rub it in a little bit, but no pun intended. But yeah, so what I did, and so what I found really interesting about this, aside from the obvious, is the bands. So I don't know how many of you follow cricket, but just bear with me for this. The bands that were handed down to Steve Smith and Cameron Bancroft were by the ICC were actually really minor. So Steve Smith got a one-match ban, Cameron Bancroft got some demerit points, and he could play in the next test. Obviously, Cricket Australia is going to, do a bit more than that. So I was watching a kind of, I guess, a podcast or something on this, and they were saying, well, why are these bans so minor? And the reason is actually because there's no clear causal relationship between using foreign objects on the cricket ball and reverse swing. That's been proven. Obviously, the players believe it works, clearly. But there's no real science behind it, apparently. So that's why it's difficult to mete out major bans for actually that offense. Obviously, cheating is another story. So what I thought I would do is see if I could find a relationship there. Unfortunately, there's no data on this anywhere. So this is a synthetic data set, but hopefully it will kind of prove my point. All right, so this is an app I've built. I haven't talked much about what Verge Labs does, but part of what we do is develop software that kind of puts things like Lime, particular packages that are really useful into your hands in a really easy to use way. So this is the app that I've built in the last couple of months. So what we do, sorry, I've lost my path. So I've created a synthetic data set called tampering. Can you see all of that? It seems like it's cut off. Probably see enough. So I've created this data set that has the type of grip. So let's just say in-swinger, out-swinger, and basic. So seamer. The speed of the ball, the age of the ball. So the kind of assumption I made here is the amount of, so what we're trying to measure is the amount of movement of the ball. The assumption I made is after kind of 20 or so overs, particularly after 40 overs as the ball gets older, the swing goes the other way, it starts to reverse. So I think I better minimize this. Very nice. Okay, that's a bit small, but that should do. Okay, so yeah, it's got a few different variables in there. Things like the weather and the pitch also have an effect on a swinging ball. So that much is known in the science, but then I've kind of added this other variable, which is whether it's been tampered. All right, so this page just allows you to fit a model. So what we're trying to fit is figure out how much swing there is, and we've got all these different factors. Now, ball ID is not very useful, but we want to look at all these other factors. Just in the interest of time, I'm not going to fit a very complex model. I looked at a few before this, and this one fit pretty well. Doesn't take too long. Model training. All right, so we've got a model here. I can't quite see that, but I think the R-squared is quite high, about 64%. So this is the overall model. Now these are some of the parameters that Lime allows. So this is the Lime R package. The Python package has slightly different parameters, but the R package is pretty much the support of the Python package, so not too different. The number of labels isn't, this is a regression model, so it doesn't matter. The number of features, let's crank that up. So just ask you, is that going up? Yeah, so showing the main features. So what it does is actually discretizes or like one-hot encodes your continuous variables if you wanted to, so that you can obviously look at the shape. And so you end up getting more features that you actually put in. The number of permutations that you can add obviously probably gives you a more accurate local model, and various other factors with your kernel, stuff like that. So run. And now we get to the actual, what data points are we going to select? So this is where Lime comes into its own. If you think about, a churn model, something like that, why is this person going to leave? Well, there could be a variety of reasons depending on which segment they are in and what factors are pertinent to that person. So obviously, similarly here, we want to look at the particular data point that is that's in question. So we want to look at reverse swings. So sorry, I might have to just stand in front of that for a second, but I want to sort by the ball age. I think that's doing it there. Is it 100? Yeah. So we got some of the kind of oldest balls here. Let's pick. I think that's a seam delivery, an outswinger. Sorry, I'm completely blind here. That should do it. We could pick more if you want. It'll just take a little longer to run. All right, so this is the kind of main Lime output you get. You also get an explanations plot, but it kind of shows the same thing. Not quite sure why they did both. And what it shows, now the red and the green just shows the direction. So big red or big green means it's important. It's picked the top, I think I specified 5 or 6 top features to pick, and it's seen kind of what effect it's had on each of those cases. It will also show the prediction of your local model against the prediction of your kind of full model. So that kind of gives you a guide as to how good your local model is at that stage. So unfortunately I can't interpret this right now because I can barely see it, but hopefully what's coming through here, things like, sorry. 5 minutes. Thanks, okay. Things like the direction of the swing, so the direction of the grip, that should have a really important effect on it. Just in common sense terms, if you're holding it as an outswinger, it should swing out, or in the case of reverse swing in. And because the amount of swing is a kind of negative if it's outswing, positive if it's in swing, that's at least how I coded it, it should have a really big effect on the kind of sign of it. So it's good to see if that's there. Things like the weather, all of that I gave quite strong factors, and as well things like randomness. So it's kind of shown these points, and the next part is looking at a kind of sensitivity analysis. So what I've done here is I've just said, all right, let's just pick the first point. So that should be just a basic normal SEMA. So you wouldn't expect a huge amount of swing, aside from random variation. And I can look at the sensitivity here. So, for example, if this one's been tampered with, if I change that to false, I can see there, I can't see the magnitude, but you can see that the prediction has changed. So what that tells you is that there's actually a factor there. So even within this local model, at this particular point, the fact that it's been tampered means that that's been incorporated in the model. So is there effect? Yes. Similarly, you can play with any of these. Obviously, as I said, the direction of swing has quite a strong effect. Things like the age, again, these have been discretized, but maybe if you change it to 20 overs or something, that might have an effect. So yeah, lots of different things you can do here, but it allows you to really understand the inner workings of this model. I didn't really talk about how I generated these numbers, but I didn't kind of just do a linear kind of equation or polynomial or anything. It was like, I made sure it was quite a kind of difficult multiplicative model with a lot of randomness in there, so that you could actually see if there's any real kind of signal in that data. It should come out here. I did look at one of these other cases which had a bit of a stronger signal, so if I just deselect this, the first one should come up. So this is this outswinger. I think if I look here, the magnitude is a lot higher. So because it's a much more swingable delivery, the fact that it's been tampered has a much bigger effect. So yeah, I mean, I don't think I've proved anything here, but certainly at least probably all understand a bit more about how I came up with this data set. So yeah, that's really it in terms of this presentation. Let me just move back to the slides. Please, if you have any questions, go ahead. I do ask that you heed by that tweet, just to kind of keep it brief. Thank you. Sure.
For your first question, for the fairness, do you think the fairness comes from models or come from the data itself?
Absolutely the latter. So the data.
So how to prove model to reduce the...
Well, so what it can tell you, so I mean, there's obviously lots of things you can do to the data to try iron out that bias. You can obviously project to different set of variables. So if there's any particular variables in there that have a particular bias, you cannot use them in the model. You can subsample your data in different ways. This isn't going to be a silver bullet, but it will at least point you in the direction of where there might be bias in your model.
Hey, so your local model seems very much predicated on the assumption that the search space for models is pretty stable, and like the global model is fairly well behaved. Interpretable models get very tricky when you start dealing with things like context or highly irregular search spaces. Have you got any ideas about how to deal with that?
So I did mention it earlier. I mean, as I did also mention that as the models get more complex, it does often get harder to interpret, obviously. But as I said, it is a flexible framework in that you can put whatever model in there as your local model. Take longer to train, but if you can kind of, bring it up to that higher level, you've got more chance of interpreting it at that local level. So where I mentioned something like a decision tree instead of a linear model there, that at least can help with some of the non-linearity if you have things like step functions.
These make sense globally, but it may not.
But it should make sense around that particular point. So, yeah, I mean, Well, again, so look, as I said, it's not a silver bullet. The reason why I presented all those other types of models as well, with anything, and I mean, that app that I just showed there, it's a beta version. What I'm actually adding to that is some of those other things, ICE, PDP, some of those other things, because just like anything, if you're fitting a machine learning model, you don't just look at one data point, you don't just look at accuracy, you don't just look at one diagnostic plot, because then you end up tuning towards that. So like this, you want to get as much of a picture as possible. But to me, when I saw Lime for the first time, I was like, wow, this is a huge step away from just doing, or step up rather, from just doing a sensitivity analysis. So, yeah.
Maybe one more question. Or zero.
Yeah, I can
Hi, I'm just curious, in your consulting work, how often do you find that people really care about interpretability, like as a percentage? Or can we just get away with the best model that works and does good predictions and not care?
Sure. So I've got two answers for you. One which I'll actually refer to Eugene. I don't know if you've heard any of his talks about how much people really care. But yeah, I won't answer that one fully. However, in terms of interpretability, I would say it's close to 100%. So it depends what you mean when you say people. Other data scientists in my team, they want me to, they want to see a good model. If it's a cow competition, who cares about interpretability? But if you're speaking to a business, and most of the time when you're working in data science consulting, you're not speaking to another data scientist. You're trying to get to a results-driven piece of business that actually enhances business value. And if they can't understand it, why should they trust it? So look, I mean, there's examples where accuracy is at a big premium. So if you're in kind of high-frequency trading or sports betting, for example, you want the best possible model, and how it works is secondary, but it's still important. You still want to figure out if you have biases, if there's things that you've missed. But certainly when you're looking at anything that's at all related to how stuff works, causality, this is a step in that direction. So people want to know how stuff works. Absolutely.
Okay, I think we're out of time. So thank you, Anthony. Before we wrap up for the night, any announcements, job advertisements, jobs wanted, exciting opportunities? There was one over there from before, two over there. Cool. Let's line up. Yeah, Greg as well. Maybe line up to get through this quickly if we've got four of you. Whoa. Five?
You're right.
Yep.
Greg Pearl, a lot of you know me, as Terry was saying, I've been around data science for quite a long time. A couple of things, thank you to Troy and Kate for videoing tonight. Videos are always up on the Data Science YouTube site, so go back. These will be up in a couple of weeks, so go back and have a look at those, all the slides and everything is there. From my side of things, yeah, obviously I recruit primarily around that data science space, as my lovely new sign tells you. At the moment, yeah, look, doing a lot of work around the AI space, do a lot of work in the fintech space, third supplier into Chalk and a couple of other incubators up there. So always looking for good machine learning, Python developers, what else, natural language processing, computer vision. But I'm also open to, there's a lot of good candidates out there, so if anyone's looking for superstars of their team, come and talk to me.
Who's next? Let's go from there.
Oh, thank you.
Winner.
Bevan Henderson, so I'm from the Star Entertainment Group. We've got an opportunity at the moment. We're looking for someone fairly senior in the data science space. So if you feel there's been a bit of a hole in your career and you've never played with gambling data, this is an opportunity to get in there. It's all around customer experience, customer behaviour, and we're just trying to build out the advanced analytics capability across the 3 casinos. So we've got Star here in Sydney and we've got the 2 on Queensland. So if you're interested, come and have a chat with me and I'll give you some information.
Jose, who else is next? Yeah, okay, cool. While you're walking up, we're also hiring at CDA. Talk to Ashley at the back or me, either way. Yeah, just got the hands up, cool.
Hi everyone, I'm Kashtash from InfoPeople. I'm a data science recruiter as well. I'm working on a number of roles at the moment. Me and my colleagues are right over there, so feel free to come and have a chat. I've got data analyst, data scientist, senior data scientist, and a director level role as well at the moment. So please come and have a chat with us. We'll be around for some time, and thank you.
One more, okay. Do you want to come up the front?
That's fine. My name's James. I'm a data scientist at Ambiata. We are hiring. Please show me what you got, but be quick because it's past my bedtime.
Anyone else? No.